Now let's look at an example of using the state space model and the transfer function model to make some assessments about the behavior of the system, and then plotting our results in using the transfer function form. We again have our simple spring mass damper system that we've been working with. We know it's a second order system. We just have these specific mass damping coefficient and spring constant values, and we'll give it a step input of 10 newtons. So first we'll make the state space model, which we've done before in the previous unit. So that'll save us some time. And now we can do some analysis with it by finding the eigenvalues of the A matrix that we create. Then we'll go into transfer function form to do the rest of the analysis. So we want to compare, are we getting the same results in the transfer function form? We should, because it's just two ways to represent our system. And then we can find the response of y. So we can jump into MATLAB and start putting this together. So here I'm first going to start by making the A matrix. I won't go through the details again. We did that last unit. But we know for the simple spring mass damper system we've looked at before that it's going to be the matrix of 0, 1 as the first row, negative k over m, and negative b over m as the second row. So in 4748, I'm just putting in the A matrix here based on the numbers that we were provided. So negative 10 is the negative k over m, and negative 2.5 is the negative b over m. So I'll put this into the workspace. All right, so we have the A matrix at this point. Now, what's new is I want to find the eigenvalues of this matrix. So I'll do that here in line 50. I'm going to save that into the variable L. So L is the list of eigenvalues, and we see they're complex conjugates of each other, negative 1.25 plus or minus 2.9j about. So the eigenvalues are complex, and the real part is in the negative, the real part's negative, so the eigenvalues are in the left half plane. So in the next segment here, I can find the natural frequency if I want, because if I know the eigenvalues, I also know the poles of the transfer function, and I know that the absolute value or the magnitude of the eigenvalues will be my natural frequency. So if I run this segment, this tells me my natural frequency is 3.16 radians per second. I won't use that directly in this problem, but it is good to know, and if I know the natural frequency, I can also find the damping ratio. Again, I won't do it for this problem, but for other problems, I might be interested in that. Now, what I can do is I can take my state space model and make a transfer function out of it. So far, actually, though, I've only made A matrix, so in this SS2TF, I need to give it the A matrix, and then the B matrix, which turns out to be a column vector in this case. It will be 0, and then 1 over m, which is going to be 0.5, so that's my B matrix. Then I need my C matrix. The only observable I care about here is y. I don't need y dot, so my C matrix is just the row vector 1, 0, and then the D matrix turns out to be a scalar since I have one observable and one input, and it's simply going to be 0. So I can run this and get the ingredients I need for my transfer function model. So I have my B, I have my A. So remember, what comes out of this is A is going to be the denominator, or really the coefficients for the denominator of my transfer function, and B is going to be the coefficients of my numerator. So it's going to be 0.5 over s squared plus 2.5s plus 10s is what this B and A are telling me. So I'll skip 59 for now and do 60. I can make that transfer function. And now it's going to print out exactly what I just said. This is the equivalent transfer function for this system. Now what I can look at is, if I look at this s squared plus 2.5s plus 10, I can find the roots of that, and those are the poles of my transfer function. So either way, in 59, that's what I want to do. I want to show the roots of the denominator, which is to say I want to show the poles of my transfer function. So I get this negative 1.25 plus minus 2.9. Again, just to revisit the eigenvalues we found of that A matrix, they are identical. And they should be. Again, it's the same system, and the eigenvalues tell us are equivalent to the poles of our system in transfer function form. Now, to find the response of the system, I'm going to be using the step. I'm going to do everything in transfer function form and use step to do it. I could have done everything in state space form. I could have used ODE 4.5 and simulated my results that way. And I'm going to get the same results. All step is doing is in the background using ODE 4.5. Just programming it with ODE45 is a little bit more cumbersome. And this one, I think it's just easier to do it in the transfer function form with the tools I have in MATLAB. But there will be times we want to or we have to do it in state space form, and that's fine. So coming down here, I've defined G. So in 61, I'm going to simulate that amplitude 10 step input. And I'm just going to plot the results, and we're going to see that we can get the results from our system. All right, so this is the output we get in our system. Now, I didn't do much analytically in this exercise. Once I knew the natural frequency and the damping ratio, which I can get from the eigenvalues of A, I could have still all in that time domain using the state space model. I could have predicted what the max overshoot was going to be. I could have predicted where the peak time was, and I could have seen whatever else I'm interested in, the 5% settling time, things like that. But the point of this exercise was to show numerically here for this example, the poles and the eigenvalues agree with each other. They both are going to be related to our natural frequency and to our damping ratio.